Hello everybody and welcome back. So last time we've worked on trampoline startup code and we did the build part for it and the embedding part for it, and we checked that we actually could read all the bytes from our trampoline startup code. I think we are going to leave it at that for now. The reason being that it will be very hard to debug that and know if it's correct or not before we are actually ready to use it. And AP initialization is still a few steps from where we are now. So the next item on the list here would be Epic initialization, but I thought that before we write a full Epic driver, we do something a bit more fun. And I want to start today by working on, so that would be somewhere here, and I'd like to start by working on the programmable interrupt timer, so the PIT. There are quite a few time or clock sources that can be used. So there's the local epic timer, there's the high precision timer, there's the so on x64 there's TSC, get a tick count from the CPU core, and on some CPUs that tick count is strictly monotonic over all clocks, so over all cores. So we can use that as a clock source. But I want to start by taking a look at the PIT, because I believe it's the easiest to work with here. And I want to use this to think up a sort of abstraction, an interface over how we want to work with all these and get them working with our kernel core. So let's get to it. Right, so programmable interrupt timer. All right, so let's see. Okay, so we have a few details here. So we have an oscillator running at this frequency here. Okay, so something about frequency division. And we have outputs, so channel 0 is connected to RQ0. Okay, so now this is good info, but it's info that I'm not going to be using right now. I'm not interested in triggering any interrupts with the timer, so I just want to set a counter and read it periodically and see that it moves, it counts down, and then when it overflows, I want to be able to reset it to go again, or have it auto reset. We're gonna see. So channel 1 is unusable. Channel 2 is connected to PC speaker. So yeah, we're going to stick with channel 0, I guess, or maybe we can write something that selects the channel we want to use. All right, so we have I/O ports, so 40, 1, 2, and 3. This one is write only. This one is, I guess, where we write the counter, and this one controls the modes and stuff like that. So, so hold on. So one byte. Yeah, okay. And then we have some modes. Square wave. I guess these are more used for sound stuff. Yeah, I think this would be the most useful one. maybe. So we'll see. Okay, so there's some sort of access mode. And then we select the channel here. Okay, fine. So initial output state, every time the mode command register is written to, all internal logic is preset, and the output goes to initial state. New reload value can be written to bit channel at any time. The operand mode determines the exact effect that this will have. Current counter, the current counter value is always decremented or reset to the reload value in the falling edge of that timer's the clock signal. The current count is not decremented on the same input clock pulse, but it starts on the next one. Okay, so these are just various hardware details about how this works in reality, but I don't think we care much about that for now. So in mode 0, when we write to the command register, the output signal goes low, and we wait for the reload register to be set by software again, after which we begin the countdown from whatever count has been set to that channel there. On the next falling edge, so that's what they said here. Okay, so subsequent falling edges will decrement the count by 1. Okay. So when we get to 0, it goes high and remains high until we rewrite to that. Okay, fine. The current count will wrap around to FFFF and continue to decrement. Okay, so that means that this internally will keep on going, but this output here will stay high. Okay, fine. So I guess this is how they trigger the interrupt. They connect this to the interrupt pin on the microprocessor, and then they have the microprocessor reset that pin whenever it sees the interrupt. Okay, fine. The reload value can be changed in low byte, high byte access mode. Okay. Okay, so fine. That's basically how. What it says is, we get this sort of clock signal that has a period of so 1 over whatever this is, 1.19 megahertz, and on every fallen edge, is that what I read? Wait, where? Okay, yeah. So fallen edge. So on every fallen edge of this clock signal here, the counter. So let's say that we have put 0x20, so that's 32, in the counter. So here it's going to decrease by 1 on every fallen edge that we have. And when it reaches 0, so when it goes from 0x1 to 0, it will trigger, so this one here to be the input, or let's call it clock. Okay. And then here the output, the channel channel 0, for example, will just go high when we reach 0. So that's what they say here. And then we'll have to do something to reset that. I think we need to rewrite the register to channel 0. So if we rewrite 0x20 to that, for example, here, it's going to reset down. This doesn't exist anymore. And on the next fallen edge, so that would be somewhere here, this is where it's going to restart counting the counting down the counter again. So that's what they say here on the next input clock pulse. So yeah. And I guess since we have a precision of this much, that means that the events are spaced by 1.193 megahertz. So that would be something like so 1/193,182, and that's 0.355. Okay, so that's 5 10 minus 5 seconds of precision. Minus 6, I believe. So that's 5-ish microseconds of precision between decrements. But I think we might be capped somehow. Not sure that this is achievable with the bit. So hold on, let me just go up here. I thought I saw something about precision. Oh, so this is not precision, this is accuracy. Okay. So do we have something about precision? And I guess the other modes are pretty much the same, except that yeah, so this one is hardware reloaded, so there's some hardware effect here that resets the counter again. The next ones, I don't really care about those. That's fine. Okay, so there's something about latching to read the 2 bytes accurately. We'll get back to that. I'm not sure we need that as of now. Some readback commands. Do we have something about accuracy or something? Yeah, I'm not sure we have anything about accuracy, but we'll try it. We'll see. So here's the plan. Let's go and make not sure we put this, but let's call this bit.zig. So we are going to need a public const. No, let's create a const bit. Should be a struct. Whoops. And we're going to create a pub function init here that takes nothing for now, does nothing here, and however does yeah, not sure. I guess we can have it be const, and we don't really need this init function here. Yeah, I think we can do this. So this would be bit, and this would be equals bit dot init or something. So here we need a public function init that does nothing pretty much. Cool. So hold on, let me think about this for a bit. We need to bring some of the things we've seen here. So ports, IO ports we have. Is this public? I guess it's public. So public ports is an enum of a U8, I guess. Is that something we can work with? Whoops, this needs to be constant. And of course, this needs that. So we were saying that we had channel 0. So channel 0 is 0x40, I believe. Is that correct? Yeah, okay. Fine. So let's get 4 of those. Oops, just 3 more. So this one needs to be 41, 42, and 43. And this goes to 1, 2, and this one is mode or command. Sure, happy with that. Right, so this is for ports. Now, let's also get something here. Public const frequency is 1193182 from memory. So let me check that. Where is that frequency? 193.182. Is that what I wrote? 193.182. Perfect. Cool. Right. I want this frequency to be U64 actually, just so that we can do a few interesting things with it. I'm also going to add. So let's go here and do public function and do call it milliseconds. And this here would take a count, or rather, it would take a number of milliseconds. Should be a U16. So let's call this millis, like this, and this would return a U16. So here I need to just think about how to do this, but let's draw this. So we have this thing pulsing at whatever this frequency here. So this one is in hertz. And what we want to know is how many ticks it needs to count a number of milliseconds. So we know that we count 1,193,000 per second. It's basically the definition of what a frequency is. So that means that we count 1.193 gigaticks per millisecond. Okay. And it means that if we multiply by the number of milliseconds we want to count, so let's say we want to count 20 milliseconds, we need, so wait, hold on a minute. No, it's not this, it's kiloticks. So, and now we multiply by 20, so that makes it 20 times 1193. I think that sounds pretty good. So return, so ms times frequency divided by 1,000. Yeah, right. So maybe we should also have something finer. So micros, and that would be same, I guess. So U16s and return micros times frequency divided by this time 1 million. Is that 1 million? Oops. Yeah, okay. Cool, so that should work. Now, what did we need to have also? We needed the sort of command bits here. So let's build that. So pub const command is a backed struct over a U8, I think. All right, so let's take a look at how that works. So we have bit 0 is mode. They're all modes, so okay. So bit 0 is a single bit, and we'll call that binary BCD. Yeah, sure. And that would be an enum over U1. That would be binary 0 and BCD with 1, or the other way around. No, that's fine. And then we have operating mode. So that's 3, 2, 1. So 1, 2, 3. So operating mode. Sure. And that's an enum over U3s. So hold on here. Mode. So interrupt on terminal count. Interrupt on terminal count, and that's 0. And then we have hardware retriggerable. I forgot one shot, and that's 1, I think. Okay. Right, so we're almost there. So we have access mode. Sure. So not sure why I've put all these in. So access mode is also an enum, this time over a U2. And here we need to, so latch count value. So latch is 0. So low byte, high byte, and both. So low byte is 1, high byte is 2, and low high byte, sure, is 3. Okay. And then we have the final things, the channel select. So channel is an enum over U2 again. Does that make, yep, that makes 8. Right, so here we have channel 0 is 0, I think. Channel 1 is 1, and channel 2 is 2. How it goes? Yeah, and then we have read back is 3. How about that? Okay, that looks pretty okay. So, let me just read this here. To prevent the current count from being updated, it is possible to latch a bit channel using the latch command. To do this, we send so hold on, what cc oh right, okay, so channel number and then all zeros. Okay, fine. And then Okay, so the current count is getting copied, and then they can be read via the data port. Has fully read. Okay, so that's fine. Okay, that's pretty good. So I think we can use that. So readback command is not supported everywhere. We're going to skip that. We are going to skip that. Okay, so now let's have a bit of fun with this. So init would be, what should we do on init? Not sure, but since we have no internal state, we're not going to initialize anything yet. However, what we are going to do is we are going to create a function to set counter to some count. Of course, this is a U16. And what we can do is, so think in here. Actually, I'm thinking that we don't really need to have this as a struct. I think this would be fine. So this here would take self as a self and would set the counter here. No, I think we need this. Yeah, we don't need that. So here what we need to do is pit dot do we have in our assembly thing here, do we have something to write to output commands? We don't. So I think that's something we need to work on. So this IO thing here will probably need to be taken and put into here for now. Yeah. So hold on, let me just mark that. So to do this was moved to arc remove. Fine. Okay, so let's go here and let's try to pick up the pace. So what we want to do is to set the counter is we want to write so set the mode right to this, and probably this, not sure. And then we want to select the channel 0, for example. And then on a second pass, on channel 0, we write the count. But what I'm not sure about is we are going to write one single byte. So one single byte, and I think if we have access mode low byte, high byte, that means that we can write the low byte first and then the high byte second. I need to learn more about that. So what is low byte, high byte? Okay, so that means, yeah, so we send both of them one after the other, and that should just work. Okay, fine. So let's first set, so out, I guess we need to const arc is import arc, assembly is arc.assembly. Okay, so let's go down here. This would be assembly.outb. The port here would be ports.command. Okay, so port.command, I guess we call that ports. Okay, fine. And here we have a value, so that value would be count with 0xff. Right. No, wait, hold on a minute. Okay, fine. So this one here would be the channel. So we need to also set or get the channel. So channel, and this would be, wait, hold on. Do we not have channels? I guess we need channels then. Pubconst channels is an enum over u2. Whoops. And this would be channel 0 is 0. Channel 1 is 1, fine. And channel 2 is 2. Wait, what am I on about? No, that should be okay. So this can be just ports. So we just need to make sure that this channel here is valid. So maybe we can call this channels instead of ports and have this be something like pubconst command port is this. Yeah, okay. This one is a U8, so let's keep it that way. Fine, okay. With this, we're happy with what we have. So channels, and this one here would be just command port, and this would be channel, so does this one. And no, actually this one would be int from enum of channel, so otherwise it's going to complain. Int from enum of channel. And I'm pretty sure we are going to need some int cast here because this supposedly wants a U16. We'll see. So we'll see when we get to that. So here we want this. And we want to get the upper, whoops, the other side here. We want to shift it by 8. Yeah, okay, that looks pretty good. So that sets the counter. And that means that we now need to set the value here for the command port. So this value here would be int from no, this would be bitcast, right, of command. And here I actually want to give this binary, going to give these default values just so that life is easier. Okay, so this one is interrupt on terminal count. This one here I'm going to set as low high pi. And channel here. I guess we're okay with that. So hold on, did I put channel on? Okay. So we might have a slight problem, but okay, that's fine. That's fine. Yeah, that's not fine at all. So let's go back to have this be ports, public fn from channel, channel u2 ports, switch channel, so 0 goes to channel 0, one goes to channel 1, 2 goes to channel 2, and that should do it, I think. Okay, fine. So this one here goes back to ports. Let me just do this here, and of course, okay, no, that's not what I wanted to do. Very nice, but it's okay. So channel, this one goes to channels, and now we can go ahead and do pubconst channels is an enum over a u2 of channel 0, that's 0, channel 1 is 1, and channel 2 is 2. Cool. This one here changes to be channels. Good. So this here changes to be channel 0. This one becomes channel 1, and this one becomes channel 2. Okay, we're getting somewhere. So here const port is ports from channel. Everybody happy? I think everybody's happy. So right, command here, we need to just set channel to be channel, or rather to be this doesn't work. This does not work. No, it does work. It does work. But that means that now this does not work. So invalid is 3. Else panic invalid channel. Okay. Fine. So what do we need now? We send this command here to set it in the right mode. We write the low value and then the high value for that count. And we should be fairly okay. So now let's try to get count for channels. Right? This one returns U16. And now here we need to find out how to read these correctly. So I think there's some, we need to do the latch thing here. Yeah, okay. So we latch so hold on, let me think about this for a second. So const port is ports from channel channel. And then we do assembly this time dot, yeah, still out bytes or out byte for the command port, and we send a bitcast of command. This time here we want access mode to be latch. Okay, and channel would be channel. Okay, very good. And now we want assembly dot in byte. So const low byte is this. The port itself would be channel, or rather, no, it would be port. Yeah. So this one here would be high byte, and we return low byte with high byte shifted left by 8. So int cast, of course, hold on, int cast as u16. No, okay, that's so we int cast this as u16 and then we move that by 8, and that should be okay. Oh yeah, hold on, this needs to be inside this. There we go. Okay, so now let's give this a try and see where we go. So hold on a minute. I want to get const count. So how many things do we want to count? Let's go for something like 200 ms. This would be bit dot millis 200, right? So let's just first of all import const. Should we do this? Yeah, sure. Import. I guess it's just bit.zig, and that's okay. So now we do bit.set counter to so channel 0, and we set that to count 200 millis, and then we so while true, or rather while let's call this variable last count is set to 0. So or we set this to count 200 millis. So while last count is positive, we read current count is bit.get count for that same channel, so channel 0, and we log sure info. This is going to be spammy, but fine. Current count is D. Of course, we need to set this to be current count, and then we set last count to be current count. Sure. Okay, sure. Let's try this. Okay, so we have a few problems here. So expected type U16 found U64. That's actually all right. So because this one here is a U64. The reason why I've put this to be U64 is because I wanted this to retain full accuracy until we do the division, and then we cast that down. So that would be int cast here. Same goes for this one here. So int cast. Cool. So let's check that that solves that. Yes, sounds like it does. So expected type. So that's 74. So here in channel, they wanted that channel, and then they got so int from enum hold on a minute. So enum from so we need to do this twice. Enum from int of int from enum, and then we should be okay, I think. Hold on a minute. That means that we need that to be done here too. Actually, it's easier to just write that. So int from enum of channel. Okay. That sounds good. So what is the other problem we have? So found U8, expected U8, but found U16. And that's actually pretty okay, because here we can just go ahead and hit this with an int cast. Goes for this one too, I think, because we can be pretty sure that this fits, since we did what needed to be done there. Okay, so expected U16, but found thing.ports. And where is that? 87, so that's here. Oh yeah, of course. So int from enum of port, and we do that here too. Rather here. Okay. So drum roll, but hopefully this builds no problems. And it does. Cool. So so QEMU, and I'm pretty sure we had something here we can use. Okay. Okay. It does not fit destination type. So where was that? Integer does not fit destination type, and that's in main. Wait, this fails? Hold on a minute. So let's do this again. So log info counting down from this, right? And then this goes to count 200 ms. All right, let's try this again. Okay, so I think this fails. This here fails. Again, I'm not sure why it should fail. So this times this. Okay, I think I know what to do here. So MS frequency, or rather count. Yeah, sure, let's do this. So as U64 at intcast of MS times frequency, right, divided by 1000. That's a U64. And here we get that and we intcast that to U16. And hopefully here we can, so somewhere over here we can go ahead and do const log is stat.log.scoped for pit. And of course we need const stud is import stud. Cool. So build this. And of course we need to use that. So debug. Let's do dms is equal to the ticks. Sure. And then this one becomes count, and then we can judge if this so ms and then count. And of course here we forgot this. Cool. Okay. Ooh. Yeah, that's not a U16. Now is it? So how come? Okay, so I guess we can review that afterwards. But for now, let's just take something that's that would fit. So let's go for 50. I guess this would need to be renamed to 50 ms. So we divided by 4. That should probably do it. We'll see. Okay. So the problem that we have is, as we might have seen this here, so we skip the thing has been reset here. We went from 14 to so 0x FFFF, and the count has just continued going. So this logic here is definitely flawed. But yeah, it's actually okay. What is not okay is that we... Oh, and we had that happen quite a few times. So hold on a minute. We can probably do that. So if current count is less than last count, we set last count to current count. Otherwise, we break. Or rather, let's do this. here we break. Otherwise, we set that to that, and we continue then. Okay, let's see. All right, let's see. Okay, so here let's just take a look at where we started and go from there. So we had this many ticks here, and we basically went down. Yeah, we basically went down all the way to. Oops, just quit that. Cool. Cool. So yeah, we went down to about 38 and then it reset. So there's actually some problems there, but we should be okay. So actually we can just take this code here. Let me just remove that and go here and do public function wait, spin wait. Let's just go with wait with a count, which is a U16, and this returns nothing. And then here we can do for last count is equal to count. And of course, we need to set the counter to. So let's go for channel 0 to count. And this goes here. And we remove the log there because that's just slowing us down. And so what do we do here? I guess that's pretty okay. That's all we need to do for now. So if we go back to main, and instead of doing this, we go ahead and do var I u64 is so 32, right? While I is above 0, we can go ahead and do I minus equal 1, right? And we can do bit.wait for count 50 milliseconds. And then here we can do done counting down from 32 times that. Sure, we'll see how this goes. One. Okay, so this overflows for some reason. Why does it overflow? 101. So go back to bit. We go to 101, and this here overflows. So get count overflows, or that's a problem. So hold on. Should I not do something like as u16? Yeah, let's just cast this to so int cast this low byte also. Okay, let's see if that helps. Okay. So we do set the counter here with the count. And we read it with the latch mode. Yeah, it's kind of weird. Okay, but fine. That should not take away from what we're trying to do here. So let's try to debug that. And actually, I want to know on which iteration it happens. So debug and iteration that, and then we can do I here, for example. Okay, so it goes down to the last iteration, and then it just panics. So what is the yeah, I'm not sure what the problem is. So we do go down. Hold on, let me just try something else here. Let's just flip this around just to make sure that it's not this that overflows. Okay, so that's not the thing that overflows, but I'm not really sure why this would change. Wait, hold on a minute. Let me just try something. Okay. Yeah, okay, so the overflow was on this line here. This is a U16 and we multiplied that. Okay, fine. Fine. Okay, so that needed to be as U64 in cast and get that there. And that was actually pretty fine before. Whoops, come on. Yeah, so this one goes to 2 and that is pretty okay. So now, should probably just, can we, yeah, okay. Oh, right, fine. So here we have measured about 1.5 seconds. So let's do 1.9 divided by 1.19. Yeah, so about 1.5 seconds that we have measured there. So if we remove these iteration thingies that slow us down, we should feel. I'm not going to try to measure this accurately, but we should feel. So yeah, it's about 1 to 2 seconds, just feeling it. But yeah. So that's pretty much it for this one. I had fun tinkering with the programmable drop timer. As always, if you've liked this type of content, please hit like, subscribe, all that good stuff, and maybe share the word. I'll see you next time. Fuck now.